So now that we've talked about Java countdown latch and Java cyclic barrier, it's time to turn our attention to the third and final type of Java barrier synchronizer, which is called the phaser. And so in this lesson, we're going to talk about initially the structure and functionality of the Java phaser. So Java phasers are yet another implementation of a barrier synchronizer. What makes it different from the barrier synchronizers we talked about earlier, countdown latch and cyclic barrier, is it allows a variable or a fixed number of threads to wait for all operations performed and other threads to complete before they can proceed. So you could use this for fixed numbers of parties or fixed numbers of threads, but it's overkill. You should use cyclic barrier for that. So really the phaser is most useful if you have a variable number of parties or threads. And the example that I gave when we talked about this earlier was having work teams build a house in phases. And so you might have a group of workers that come and do the foundation. There might be 6 of them. Then in a week, you might have another team that comes and does the framing, and there could be 4 of them. And then you have people who come and do the roofing, and there could be 10 of them or whatever. But the point is that there could be a variable number of workers per phase, but there would be phases. And so you wanted to make sure that everything was done before the next phase began, but you wouldn't always have the same number of workers or even the same number of, even the same workers working on each of the different phases. In fact, you'd probably have different workers and different numbers for each phase. We can use phasers for the cyclic entry and or exit barriers. So it covers the full gamut of different barrier types that we've talked about throughout these lessons. And of course, the key thing here is the number of parties can vary dynamically. For fixed size barriers, it's probably overkill to use a phaser. You might as well just stick with countdown, or with either with countdown latch if you don't need cycles, or with cyclic barrier if you need a fixed number of threads that work in cycles. Phaser, like countdown latch, phaser, like cyclic barrier, does not implement any interface that's important for our purposes, nor does it apply the bridge pattern. It uses its own implementation that's orthogonal to the pattern that we talked about, or it's orthogonal to the abstract queued synchronizer framework, and so on and so forth. So it's its own thing. Instead, what it does is it defines a bunch of fields that it uses to implement the phaser semantics. And this is a really interesting implementation. It essentially stores a bunch of info in a long, volatile flag, which it calls state. And the state representation is used in order to store this information in 4 bit fields that are all kind of put together into that one state variable. So here are the fields that are used. There's one that's called unarrived, and that's the number of parties that have yet to hit the barrier. So it's between 0 and 15 bits that do that. Remember, a long has essentially 64 bits. So 0 to 15 are for unarrived. We have the number of parties, which are the number of parties to wait for before advancing to the next phase. Those are bits 16 to 31. We then have the phase, which is the generation of the barrier. Those are bits 32 through 62. And then the final bit in this bit field is terminated, which is set if the barrier is terminated. And the thing to keep in mind here, of course, is that they're trying to pack all this information together in order to save space. They could have, of course, also just used a bunch of different fields, which would have given them more precision, probably would have been a little faster, but this is the way they chose to do it. And another reason why they did all this, why they made it like this, was so they could pack all these things into a single volatile long that can be read to and, or rather, written to and read from atomically using some of those cool compare and swap operations we've talked about before. So this makes things super optimized from the point of view of synchronization, even though the bitwise operations might be a little bit slower than if we were doing them on unpacked fields. So the real motivation here is to make this work very efficiently in a concurrent environment. And it's probably the right thing to do. Well, obviously the right thing to do because people who wrote it were very smart. So that's the end of the overview of the structure and functionality of a phaser. At this point, you probably have very little idea of how to use this thing, but that's okay because we're about to cover that in the next couple of videos.